I've identified this one as Chapter 13, brown. Now, of course, the slides will come from my Chapter 12, I think. Since I'm extracting my slides, no, 11, excuse me. My Chapter 11, your Chapter 13. So just so there's no confusion, if you need to find information on this topic, it'll be in your Chapter 13. So let me share. Let's see, I just have to find them. Here we go. And that, of course, is why my slide backgrounds don't look anything like your textbook, because they're not from your textbook. Chapter 11. So we're going to look at properties of solutions today. Remember, solutions are a special kind of mixture. And in fact, they're a homogeneous mixture. A homogeneous mixture or a solution will have the same composition of the various parts, no matter where you look. So take a sample from here, a sample from there. And if it's two components, then you'll have exactly the same ratio of component A and component B. But these components can be in various states. And the other, by definition of our terms here, the solvent is the major component, and the solute is the minor component. Okay, now I should say the minor because you can have more than one solute in a solution by definition, but you can only have one solvent. So this is limited to one major component. Now this, under most circumstances, this definition works no matter what the concentration of solute in the solvent is. There are some cases where you may start off with a major component solvent, but if you keep adding the solute, you'll exceed the amount of solvent. You'll be more than 50% solute. In those cases, we retain the definition of solvent as the major component when you start. A perfect example of that is sugar water. When you dissolve table sugar in water, everybody knows that hummingbird feeders, we usually put 50-50, you know, a cup of water and a cup of sugar. But you can start off lower than that, and you can go much higher. You can, saturation, which I'm using a term I haven't defined yet, the most that a solution of sugar water can hold of sugar is very high, on the order of 80 or 90%. But we still say water is the solvent. Okay, so these are various types of solutions based upon the phase. So air that we breathe, even natural gas straight out of the well, is a homogeneous mixture of various gases. Air is predominantly nitrogen and oxygen, with some other minor components in it. But the state of the solution is a gas, of course, and the original state of the solute and the solvent, either one, is gas. So you put two gases together and you always get a solution, a homogeneous mixture. Because the distance between molecules in a gas is so far between, there's plenty of room for everybody. And they interact, but they interact very weakly, the molecules, that is. So when you put two different ones together, they generally behave just as if they're billiard balls. They just fly around, and sometimes they strike each other, sometimes they don't. But there's plenty of room for everybody. Now, antifreeze or vodka, any type of booze, you start off with a liquid solute and a liquid solvent. So the solvent for alcoholic beverage is water, and then the solute would be ethanol, plus some other things. Antifreeze would be water, would be the solvent, and let's see, the solute would be, oh, my mind's gone blank. Ethylene glycol is the compound it's called. They're both liquid to start with. Put them together and you still got a liquid. Brass. We normally don't think of alloys of metals as being solutions, but brass is an example of a solution where you start with a solid solvent, which would be copper, and the solute would be nickel. It's a minor component. And of course, you have to melt them to get them together. But once they solidify, you have a solid solution. Carbonated water. You start off with a liquid water, it's a solvent, and you dissolve a gas in it, carbon dioxide. And then the state of the solution is liquid. In other words, you don't know that there's a gas in there until you do something to it. Like crack the top off of your pop bottle, and you know there's a gas in there because it spurts on you. Seawater or sugar solutions. These are examples where you start off with a liquid, in this case water, and the solute then is, in the case of seawater, is some salt or combination of salts, primarily sodium chloride, but you have calcium and magnesium chlorides in there and some potassium chloride. Sugar, of course, is just sucrose dissolved in there. So the solute is a solid, but once it goes into solution, the solution then is all liquid. And one way to tell that you have a solution, particularly when it's a liquid and you have the potential for solids in your solution, is use the Tyndall effect. So if you have a beaker of what you think is a solution, you just need a flashlight, a light of some kind, and if you can see it on the other side, let's see. Well, you will see it no matter what you have. But if it's a suspension and not a true solution, suspension is a heterogeneous mixture. If it's a solution, then you won't see the light beam in the liquid. If you're looking through a beaker, you won't see the light beam. You'll see it going in, you see it coming out, but you won't see it inside. But if it's a suspension where you have these, even the very finest particle sizes suspended in the liquid, then you'll see the light beam, dispersing the light beam, bouncing off those little particles. That's called the Tyndall effect. And then lastly, we could have, strange as it may seem, you could have a solvent that's a solid and a gas dissolved in it. And then, of course, in this case, you have a solid solution. And perfect example of that is hydrogen in platinum. Now, why would we want to put hydrogen on platinum or in platinum? Well, platinum is a catalyst. That is, it accelerates and favors a certain reaction. And until recently, unsaturated oils and fats were reacted on the surface of platinum to hydrogenate them. In other words, the unsaturated bonds become saturated with hydrogen. And they do that for various physical reasons, and I won't go into that right now. But in order for it to be accomplished, you have a solution of hydrogen, a gas, in a solid platinum. Another example is the catalytic converter in your car. Inside the catalytic converter is packed with these little ceramic beads, and on the surface of the bead is platinum or various other rare earth metals that catalyze the complete conversion of oxides of nitrogen and partial oxides of carbon into carbon dioxide and nitrogen gas and water. So in order to do that, the gases that are flowing through the tailpipe enter the platinum alloy, and there they are, the reaction is promoted for complete conversion of those partial combustion products into less polluting versions, I should say. So that's a gas dissolved in a solid. Now, we need to have a way of expressing concentrations, right? If you're going to have so much of this in a certain amount of that, we need a way of expressing that concentration. And one that's very common, very popular in the sciences is called molarity. Molarity. And it's abbreviated with a large M. We can use a large M primarily because there are no elements in the periodic table that are identified with just an M, a big M. And any other place, the other place that you would use a big M is as a prefix for our unit of measure. M stands for mega or a million. But when it's sitting by itself, nothing else around it, it means molarity. And we define the solution, the concentration of solute in the solution based on this measure. We have moles of solute per liter of solution. Okay? So if we have a liter of solution and we know that it's 1 molar, we know in that liter of solution there is exactly 1 mole of solute. Okay? We'll talk about preparing these a little bit later. We'll just run through the definitions right now. Another common way of expressing concentration is mass percent. Okay? So mass percent follows a standard of expression that's common to percentage. Percent just means parts per 100. Okay? So if we have 1%, it would be 1 part per 100 parts. The problem with that is mass percent in itself, I mean, if you just have 25%, that's a dimensionless number, even though we have this expression out here, because you don't know whether the top part was grams and milliliters, or grams and grams, or 100 grams, or 100 milliliters, parts per 100, 1 part by gram per 100 part by milliliter, or you could have milliliters per milliliters. So when we say mass percent, we're locking it in to 1 unit of mass per 100 units of mass. So whenever you see percent, if percent is not accompanied with that little definition, you know, what type of percent is it, then you either have to look for convention or make an assumption, or you can't use it. So mass percent, and by that we often mean weight also, weight percent, is sometimes given with this parentheses. So we might say, like I said, 25%, and we may in parentheses say weight, weight, or we might say mass, mass, to identify what it is. But what you do is you identify the mass of the solute that's contained in a certain mass of the solution, right? So the mass of the solute divided by the total mass, and that includes the solute, the total mass times 100. Let's see, mass of the solute divided by the mass of the solution times 100. Okay, mole fraction is another useful expression of concentration, and it has this special X form. Actually, that's a Greek letter, capital Greek letter. Now, if we say the mole fraction of A, then what we mean is the number of moles of A in the total moles of solution. Now, have we defined mole yet?
Yes, we did in the first part of the class.
Okay, good, thank you. I teach too many classes, I can't remember when we covered what.
You're fine.
So this is mole fraction, and it's just that. It's a number less than 1. So you can have a mole fraction of A of, say, 0.2. So 2/10 would be mole fraction of A. If there were anything else in there, you might have a mole fraction of B or C or D. It could be as many as you need, but all the mole fractions together must add up to 1 because they are fractions. They have to add up to the whole. So if mole fraction of A is, let's just, for example, say it's 0.2. What's the mole fraction of the solvent? The solvent would be 0.8 mole fraction if those were the only 2 components. Okay? Now we have one more that's used. It's called molality. Okay? And we say a solution is a certain concentration molal rather than molarity. It's not molarity, it's not molar, it's molal. The difference is, whereas molality, molarity expresses moles of solute per liter of solution, molality, which is designated by a small m there, is moles of solute per kilogram of solvent. So there are 2 differences between molarity and molality. When we moved move to molality, we're still talking about moles of solute, but we're referencing it to a mass of the solvent, or the mass, well, mass, just mass. And then not only just the mass, it's not the mass of the solution, it's the mass of the solvent. Now, where would we need to use something like that? Notice that molarity is based upon volume of solution. And what do we know about liquids when you heat or cool them? They change volume.
Yeah.
Right? So if you're going to use an expression for concentration in an operation where you're expecting the temperature to change, you may want to think about using molality instead, because its expression is free from changes due to temperature, because the mass will not change due to temperature. And of course the moles won't change either. That's, you're counting a certain number. Okay, so those are the main types of expression for solution composition. And I've got separate slides, and let's see, for molarity, if we have 1 mole of sugar and 125 milliliters of solution, what's the concentration in molarity? So here you have to pay attention to your units. Close attention to your units. Oh, wait a minute. This is 214. We covered moles in 213. Now that I recall. Okay. So I forget where I am. Okay, so if we're gonna calculate molarity, we need the moles, and sometimes I use a symbol for moles as little n, right? Without the zero. Put the zero up there, that means neutron, but the n, little n without, means moles. So we want moles per unit volume, and we have what, 1 mole, right? So that's your solute, and your volume needs to be in liters, right? But our volume here is given in milliliters, so we got to convert that into liters. So how do you do that? Well, if you know the units of measure and their relationship, you can do it in your head. I just move it 3 places over, and that's how many liters you have. Or if you need practice with dimensional analysis, you can use a conversion factor. Right, 1,000 milliliters per 1 liter. So the milliliters cancel, leaves you with liters, and you divide this by 1,000, which gives you that value. And then you, of course, you plug it in here. Liters. And you just, actually, you just take the inverse of 0.125 on your calculator. And it turns out we have 8 molar solution, which is pretty concentrated. Very concentrated, as a matter of fact. Okay. One other point is that that is a formula, which means if you can substitute values for 2 of those, the third one is solvable. You don't have to always use it as this is the unknown and those are the knowns. You could have this known, that unknown, and solve for that unknown. So in this problem, we have 10 molar solution. And what else are we given? 2 moles of sugar. And we want to solve for volume. What volume of this solution do you need to have 2 moles of sugar? and then you just solve for V. So we bring V over here and put 10 over here, and the volume then would be 1/5 or 0.2. Yeah, 0.2 liters. Now, just for fun, how many milliliters would that be? 3 places to the right. 200 milliliters is 0.2 liters. Okay. So let's say you have 2 solutions, separate solutions of sodium hydroxide and potassium chloride, and you make them by dissolving 100 grams of each in 250 milliliters. What's the molarity of each one? So how do we do that? Well, let's put our information up here on the board first. We have 100 grams of sodium hydroxide. We also have 100 grams of KCl. Okay, and we're going to put that in 250 milliliters, each of them, in 250 milliliters equals your volume. So the volume's the same for both of them. Now, do we have enough information to solve the problem? No, we got to dig. We got to look for more information. Why? Because mass does not satisfy the conditions for molarity. So what we need to do is find out how many moles does that represent. So we need a conversion factor that will convert grams into moles, right? Whenever you see that ratio, grams on one above, moles below, or grams below and moles above, think molar mass. That's what that means. So we need the molar mass of sodium hydroxide. So we got to go to our periodic table, and we say, we give a calculator. Sodium is 23.00 to 2 decimal places. Oxygen is, I have them memorized, 16. And hydrogen is 1.01. So that's 40.01 grams per mole. Okay, how about KCl? That's going to be different, isn't it? What's potassium? Let's look at my chart. 39.10. And chlorine is 35.45. So that's 74.55. Okay? So now we can calculate the moles of each. See, I still got this one in my calculator, so I'm going to do this one first. That's 1.34, 4 places, 1.341. Okay, and this one, let's see. Yep, is 2.499. Okay, now we can calculate, except that's not in liters, is it? So we need 0.2500 liters. Now, concentration is moles per liter. So we divide this one by that, and then we divide this one by that. So let's see, 2.499, enter 0.25, divide. So that's 9.996 molar. And the other one is, let's see, there it is. Yeah, I better do this. 4. There we go. Divide by 0.25. And that's 5.364. So we had to go through several steps to get where we were going. And there were several skills involved, but actually the most important one was keep track of your units. Let the units guide you to the answer, in addition to the formula, of course. So they're rounding that off to 3 places. I don't see why, because you've got 4 places here. Right? We should be able to report 9.996. And 5.37, well, they use different values. I think they come up with a slightly different value here. But if you run into this problem on a test, you pick the best answer, right? So you've calculated 5.36, and 5.37 is the only one that's close to it. Pick that one. Okay. Mass percent. This is fairly simple, actually. But it's useful, not just in solution chemistry, but it also is useful in analytical chemistry, mass percent. Because when a new compound is submitted for analysis, the first values that will come out of the analysis, usually a mass percent of each of the elements in that compound. That's another problem, but they're very closely related. In this case, percent by mass in this solution, you have 5.5 grams of glucose. And 78.2 grams of water. But we're not done yet, right? Definition of mass percent is mass of the solute per mass of the solution. And what's still in the solution down here? Right? Once you put them together, that becomes part of the whole. So don't forget to put that in there also. And then times 100. And rather than calculate that, you should get about 6.6%. Okay, mole fraction. Let's see, are they going to give us a problem to work? Yeah, okay. Mole fraction. A solution of phosphoric acid was made by dissolving 8 grams of H3PO4 in 100 milliliters of water. Calculate the mole fraction of H3PO4. We have to assume a certain density for the water and the solution. So moles of A per total moles. So we're going to have to calculate the moles of both of them, water and phosphoric acid. And then to get the total moles of the solution, you just add the two together. So we got 8 grams of phosphoric acid. And we need to convert it to moles. So we got to cancel grams and leaves us with moles. There the light bulb comes on and says molar mass. So what's H3PO4 molar mass? We have to go back to our periodic table. 3 times hydrogen is 3.03. And then phosphorus is 30.97. And then we have 4 oxygens. 4 times 16 is 64. So that's 98.00. Okay, divide that into 8. And we get 8 let's see, 3 significant figures. So I can keep 2 places, 0.0816. Okay, now we need moles of water. And we have 100 milliliters of water. There's no direct conversion of milliliters to moles. We got to find out the mass of water first. So this is a dimensional analysis problem where you have a chain conversion. And the density is where we're going to get grams out of this. Right? Okay, so that's canceled. Now we need water, molar mass. So I just happen to have it memorized. H2O is 18.02. Why? Because 16.00 for oxygen and 2 times 1.01 for hydrogen together makes 1802. Now we can find out how many grams that is. Oh, and moles. Right, cancel those. There we go. So we have 100 divided by 18.02. 5.549. Now we can do mole fraction. So we have so many moles of the solute, and then we have moles of solution, which is 5.549 plus 0.0816. Okay, and that's moles on top, moles on the bottom, moles cancel. So mole fraction is a dimensionless number. Whenever you're dealing with a dimensionless number, it's usually the result of a calculation. You need to know where it came from, because if we just reported the fraction, then we wouldn't know what it means. But if we identify it as mole fraction with that fancy X equals this number, then we know what it means. Okay, so let's finish the calculation. Let's see, 0.0816, and add that to 5.549, and then divide. So I get, let's see, 3 significant figures. I get 0.0145, rounded off. And that's equal to the mole fraction of phosphoric acid. Okay, I need to change markers. That one's getting faint on me. Okay, so these problems require multi-step, some of them. So there's our molality definition, and here's our problem. Oh, we got the same problem now. We want to say, if this is mole fraction, what does it look like as molality? Right? So let's see how much of this we can keep. We want molality, moles of solute. We'll keep that. Right? Now we need how many kilograms of solvent, how many kilograms of water. So we'll erase this stuff. So let's convert 100 milliliters to kilograms, right? So that's grams. Now we need kilograms. Okay, so we just need to say that's 100 grams. Oh, it's a tenth of a kilogram. Okay, now we can do the calculation. 0.0816 moles divided by 0.1000 kilograms of the solvent. Right? So that's 0.816 molal. Okay. So now we know how to express concentrations. Those are more closely akin to laws. We're just explaining this is how it works. What we're going to get into now is why do solutions form? Well, actually, we're going to get into a little more mechanics first. There are various steps that we envision for formation of a solution. And like I've said before, nature just does what it does. And this is how we rationalize what's happening. It doesn't really happen this way, but in order to wrap our brains around and explain how a solution forms, we take it in steps. So the first thing you have to do, if you're going to form a solution, is you got to separate the solute molecules from each other, expand them. If they're attracting one another, you got to pull them apart. And that's usually the case. So that requires an input of energy. So for the first step, separate your solute. That means that it's going to require an input of energy, which is negative. Right? Remember enthalpy. Positive. The enthalpy of that step would be positive because you're putting energy in. Right? Remember, the system is the reference point. So if we put energy into it, then it's a positive enthalpy amount of energy. The second step, you've got to overcome the intermolecular forces of the solvent. In other words, you got to make holes, places for the solute to go. So you separate the solvent. And that's also endothermic. Put energy in. Okay. Now, once you've got those things have happened and the solute molecules begin to interact with the solvent, so you interact solute with solvent. Let me not put it that way, like that. That's usually exothermic, right? When they start to form bonding, interaction, and I'm saying this bonding on a intermolecular scale, right? So they could have dipoles, they could have dipole ions, they could have London dispersion interactions. You get some of that energy back. So that step is exothermic, because the closer they get together, they are higher energy farther apart, lower energy close together, so they give up some energy in the process. And the overall delta H for all three of these processes depends on how much did you have to put in here, here, and how much did you get back there. And then the balance, whatever that happens to be, will tell you if the overall enthalpy of solution is positive or negative. So for some solutions, you put two things together and you get a whopping amount of energy back. So that will be exothermic solvent formation. And that's typical of strong acids and strong bases going into aqueous solution. They always get hot. There are some solutions like, let's see, ammonium acetate, I think. When it goes into solution, the solution gets cold. So that means you had to put energy, a lot of energy in here and here, and you got almost nothing back. So it absorbs energy. And that's the foundation for cold packs in the hospital or medical profession, where you break a little capsule inside the bag, you shake it up, and that heat of solution will make it cold. Of course, you can have the other way. You can, whatever's in that capsule going into solution can make it hot. So you have hot packs and cold packs. Okay, so this is an explanation with visual effects. So there's the first step, there's the second step, there's the third step. When you add them all together, you finally get a solution. Okay, so the first two are endothermic. Third one is exothermic. It just may not be very high exothermic, but it's a little bit. And the balance of those determines whether you have endothermic or exothermic. Okay. And this is another way of expressing it. These two require energy input like that. And then you get energy back when you go for this step. So overall, there's your delta H, your enthalpy of solution. And this is another possibility. So if it goes down like that, that means you get energy back. It's exothermic. If the difference is up like this, then it's endothermic reaction overall. Okay, I'm going to leave that up there for a second. Explain why water and oil do not mix. Okay? So, if we put energy in to separate the hydrocarbon molecules of oil, it doesn't take much, right? Because oils are nonpolar. They don't attract each other very strongly. So this is very small. This one's very large. Lots of energy required to break the intermolecular bonds of water molecules. So large input there. Overall, a lot of energy required to go in. But what about the energy you get back? Do hydrocarbons and water molecules attract one another? Well, the answer to that is no, because water is polar and hydrocarbons are nonpolar, so there's not much influence, that there's no attraction, except for London dispersion forces, which are extremely small. So you don't get anything back. Okay, so that's a long-winded version of why oil and water don't mix. And this is a chart that came out of the textbook I'm using. And it looks at the various combinations. If you have a polar solute and a polar solvent, right, then it takes a lot of energy to pull those solute molecules apart. It takes a lot of energy to pull the solvent apart. And then when they interact, because they're both polar, you get a lot of energy back, exothermic part. But the difference between this summation and that sum is very small difference. And the outcome is a solution will form. Let's look at the other possibility down here, nonpolar solute and nonpolar solvent. Right? So for both the solute and the solvent, it takes very little energy to make the whole or to separate the solute molecules. And then they don't interact very strongly because London dispersion forces, that's all they've got to go on. So you got small, small, and small, giving you an overall small difference, right? And a solution will form there as well. Now, what are the other possibilities? Well, you could get one nonpolar and the other polar. Right? So nonpolar solute would be the oil, polar solvent would be the water. And like I said before, it takes a little bit of energy to break up the nonpolar solute, takes a lot of energy to break up the solvent, water. But when they interact, you don't get much back. So the delta H is large positive. It takes a lot of energy overall to make it happen, which is why, especially at room temperature, you don't get much of an interaction. See, there's my pointer. Keeps disappearing on me. So no solution is likely to form, unless, of course, you increase the temperature to a huge amount so that you can put all that energy in there that's needed. And where would we see that in a practical application? Well, if you've ever seen an old, dirty automobile engine cleaned with a steam spray hose, then you see that hot, very hot water will dissolve oil. It doesn't just blast it off there, it actually dissolves it. So it's temperature dependent because of this summation has to be very large input of energy. The other way around, if the polar solute requires a lot of energy to break it up and the solvent doesn't take much, then the overall is a small, the overall is a large difference. So it takes a lot of energy to break up the solute, in this case, rather than the solvent. But the net is still, you have to put a lot of energy in to make it happen. And that's why those solutions don't form either. Okay, that was a long way around the barn. But, and I better keep track of my time too. I got another hour. Okay. So if we generalize, starting at the bottom, working our way up, that's why we say like dissolves like. So what do we mean by like? Polarity. If the solute and the solvent are polar, you're likely to get a solution. If the solvent and the solute are nonpolar, you're likely to get a solution. If they're opposites, you're unlikely to have a solution. So in my mind, that begs the question, how do you get your clothes clean? Because most of what makes your clothes dirty or attracts particles and dirt are the oils that come off your skin. They saturate your clothes and they attract dust and dirt and even skin off of your body and whatever. So how do you get that stuff out of there? Because water won't dissolve it, right? Those oils are nonpolar and water is polar. So we use soaps and detergents to bridge the gap. So let's say you have oil here in your clothes and you have water over here in the washing machine tub. And to get them to work together, you bridge the gap with a molecule that is long enough and has dual nature. So on this end, the molecule is nonpolar. And on that end, is polar. So this side of it dissolves in water and that side dissolves in oil. And that's how you get oil to remain in the water in your tub in solution long enough to get rushed down the drain. Now the chemistry of this varies. If it's soap, then this is a long straight chain hydrocarbon. Just carbon, 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 carbon in length, and then hydrogens everywhere else on the outside. Makes it nonpolar. On this end, for soap, you have a like that. That's a carboxylic acid thing, and you'll see that in all fats that have been saponified. So if you have a grandparent that makes their own soap, I've had students that tell me they still do. They make their own soap. In fact, I had a student that made his own soap. You take fat like lard and you saponify it, which is a fancy word for you mix in sodium hydroxide base, drain cleaner. And what it does is it breaks these molecules off of the fat structure and leaves you with this polar end and a nonpolar end. And that's how soaps work. Detergents are a little more complicated. Instead of having this ionized end down here, which can lead to formations of scum in your tub, they're non-ionic. That is, they have polar ends, but they're not complete ions. So that's a topic for another discussion. If I could ever get enough students to sign up for organic chemistry, then we could have that discussion. But for now, that's as far as I can go in the time we have. Processes that require a lot of energy tend not to occur. Doesn't mean they won't occur. It's just they're not as probable. And another factor, another way of explaining this is in terms of probability. What's the probability of a state actually occurring? And for unlike solute and solvents, the probability is very low. And we'll reintroduce this subject when we get to the discussion of entropy later in the course. Okay. So what factors affect solubility? Well, it depends on what you're trying to dissolve in the solvent. Solute and solvent characteristics and their states, right? So generalizing, we can usually discuss solubility in terms of polarity, right? We've already done that. And it doesn't just happen for liquids and liquids or solids and liquids. It can happen for any phase type. For Henry's law, we're actually talking about gases dissolved in liquids. So it's a little more restricted in its application. And we'll talk about that in just a second. Another effect is temperature. Usually, if you increase the temperature for a solvent, the solute will be more soluble in it. And that's for 99% of the potential solutions that you would form. Rarely, you get the opposite effect. Decrease the temperature, and the likelihood of forming a solution increases. But most of the time, increase the temperature increases solubility. Okay, structure effects. Okay, we're going to take this first one and break it down. So, useful terminology. If a solute is said to be hydrophobic, that means, well, literally means afraid of water. So it won't dissolve in water. That means it's nonpolar because water is polar, and it's will not dissolve. Hydrophilic, on the other hand, is water-loving. Hydro, water, and philios mean liking or loving in Greek. So these compounds are generally polar, and they dissolve well or easily in water. And this is a good place to start because in general chemistry, we're primarily concerned with aqueous solutions when we're conducting reactions. If anything's going to be in solution, it's usually in aqueous solution. We don't get to non-aqueous solutions until you start talking about organic reactions, and that's a completely different course. Okay, for Henry, we can express, and remember this is a law, and in the first general chemistry course, we discussed the difference between a law and a theory. A law just defines relationships. Like if you have these sets of circumstances, you'll always have this outcome. And in this case, we're expressing it in terms of a formula. So if you want to know the concentration of a gas in a liquid, and by the way, as a preliminary statement, the pressure has very little effect on solids or liquids being dissolved in one another in any combination. Pressure really is only applicable in terms of gases in liquids, or actually gases in solids, but Henry was working with gases and liquids, so we'll stick to that type of solution. But the concentration can be calculated if you know the pressure of the gas above the solution. Then you can say, all right, if the pressure doubles, the concentration of the gas in solution will also double. And you need a constant. This is a proportionality constant right here. So whatever that is, and that's characteristic of the system, the gas and the liquid, the solvent, both. So it's very restricted in its application. C equals Kp. So that's the initial formula, but there's a version of it that allows you to do the calculation without knowing what K is. All right, and remember, well, let's see, our discussion of gas laws back in the first semester, where we had the gas law and then we had a version of it where it was before and after. Well, you can do the same thing with Henry's law, because C equals K P. So then if we put the K on one side, then we can say C over P. So the concentration divided by the pressure is equal to your K. But if we have, under the beginning circumstances, we have concentration and pressure known, then we do something to it. So we change the pressure from this one to that one. Then we can calculate that fourth value, because we know this two and we know that one. We got one unknown. They're equal to that, so they're both equal to each other. And you can calculate the concentration after you change the pressure. Okay. Notice that we're talking about here about partial pressure. So the concentration of the gas in the solution is based upon the pressure of that gas alone. If it's a mixture of gases, then the concentration will vary depending on the gas that's going into solution. For instance, nitrogen is reasonably soluble in water, or let me be more specific, in methanol. And I'll tell you why I said that in just a minute. But helium is not very soluble, even under high pressure. So one way to expel nitrogen from your solution of gases is to bubble helium through it. And helium drives the nitrogen out. It displaces it, but it doesn't stay behind. And there you have a degassed solvent. It's got a special term. We call it sparging. And we used it, I've used it, in operating high pressure liquid chromatography equipment. So in short, you have a tube packed with an absorbent, and you push your solvent plus your sample through it, and chromatographic effects separate your sample into its components. But the solution going in is under very high pressure, 50, 60, 70, sometimes 100 atmospheres, very high. So what does that do? Well, very high pressure means very soluble, high solubility for the gases. So what you want is you want to exclude all gases that are particularly soluble, because what happens at the other end, on the other end of the column, the pressure is immediately 1 atmosphere. It goes from 100 to 1, and all those gases in solution go, they just bubble out. And that would be devastating for your detector, because the detector's on that end. And you want to preserve your equipment, so you want to get rid of any dissolved gases that you can from your liquid. Now, that's one way of doing it. There are alternate ways, and we don't have time to talk about those now, but that just illustrates the solubility of gases is variable in solution. So how do we explain that solubility? Well, what happens when you, if you have a liquid with a gas over its space, a headspace, and it's reached equilibrium, so the molecules of gas are dissolving and evaporating at the same rate. Then if you decrease the volume, you add pressure. So we increase the pressure here based upon Boyle's law, pressure-volume relationship. Then what you end up with is the same number of gas molecules confined to a smaller volume. This is a Le Chatelier's disturbance, right? We have disturbed an equilibrium system. So what is it going to do? It's going to respond, and temporarily the dissolution rate, the rate at which gas enters solution, is increased to a rate higher than the gases leaving the solution, until you have reduced the number of gas molecules in the headspace to a point where you're at equilibrium now again. Okay, how about temperature effects? And this is for aqueous solutions. Just to say that most often, increase in temperature increases solubility, more gas in solution. Well, actually, we're talking about solids here too. So the solubility of the solid in water increases with temperature, except for a few notable exceptions. So that's for solids. For gases, it's just the other way around. As you increase the temperature, the gas becomes less soluble in water. So as an example, what happens when you put a pan of water on the stove to boil? Right? It gets warm, of course, and you can tell when it's starting to steam, even if you don't see bubbles, because you can see the vapor rising from the water. But before you see that, you see little bubbles forming inside the water on the surface of the pan, on the inside surface of the pan. That's not water evaporating. That's not boiling. That's the dissolved gases coming out of solution. As you increase the temperature, they become less soluble, so they degas. And only after that do you raise the temperature high enough to boil the water. Now let's see if we're going to get an explanation for that. Let's see. No. So why would gas be less soluble? Well, think about it. What are you doing when you add heat to a solution? You're increasing the kinetic energy of the molecules, right? For the liquid, for the solvent, that increases its vapor pressure, the amount of water that's leaving the surface. But it also adds energy to the molecules of dissolved gas. So what do? Well, you're disturbing the equilibrium again, right? You're adding energy to those dissolved gas molecules, and they're leaving the surface of the liquid more rapidly than they are returning. So you're essentially decreasing the solubility of the gas because you're adding energy to those molecules and forcing them to leave the solvent. Okay, let's see. We're still good. I've got another 45 minutes. The solubilities of several solids as a function of temperature. Okay, so we've got, see, most of them, as the temperature rises, the solubility increases. On this axis, we've got solubility as expressed as grams per 100 grams of water, right? So this is a unit of solution concentration that we didn't introduce before, but it's similar to the mass percent. Well, in fact, it is. It's a mass percent. Yeah, we did talk about it. Yeah. Parts per 100 parts. So many grams of solute per 100 grams of solvent. Okay, so sucrose, sugar, increases solubility as the temperature goes up, right? That's why when you're making iced tea in the summer, you don't cool the iced tea down first and then add sugar, right? It takes it forever to go into solution. You put the sugar into the hot tea before you dilute it with your ice water. So you make up a double constant, this volume with your tea bags, and it's hot, boiling. And once you've soaked them, then you pull them out, and then you add your sugar. And then you add about the equal amount of cold water plus ice to double that volume, and there you have your iced tea. At least that's the way we do it in the Deep South. So what other things increase solubility with temperature? Like potassium nitrate is extremely soluble. Increase in solubility with temperature increase. There's sodium nitrate, increased solubility. Sodium bromide, slightly more soluble, right? So you have different responses to temperature depending on the different compounds. Potassium chloride is more soluble. These sulfates here become less soluble. Right? So an explanation of that is beyond me at the moment. It's not easy to explain that, even for those who study it for a living. It just happens. Let's just put it that way. Solubility of gases. Okay, so here we have, as the temperature increases, the solubility of methane goes way down. Oxygen goes way down. Carbon monoxide down. Nitrogen down. Helium is lower than all of them at any temperature. So that's why we sparge our solutions with helium. There might be some gas in the methanol. We call it mobile phase, moving through the chromatography column. But there's not very much. So on the other end, a little bit comes out, but it's not enough to damage the detector or influence the readings. Okay. What happens? This is an interesting experiment to conduct. I've done this before as a demonstration. If you have a bell jar and you put 2 beakers in here, and one of them is pure solvent, pure water, and the other one is a concentrated solution of something. It could be sodium chloride, it could be potassium nitrate, it could be sulfuric acid is a very effective one, and it happens very quickly with that one. So that sometimes that's what we use. You just have to be careful handling it. So if we put the high concentration over here and the low and the solvent, pure solvent over here, what you notice over time is that the solvent disappears and the solution volume increases. So what's happening? Well, there's no direct contact between the two, so everything that happens has to happen in the gas phase. So what happens is you may start off with an equilibrium of each one, but then what happens is the equilibrium is continually disturbed by the water molecules. If they try to return to the water solution, they do at a certain rate. But if they come over here, they enter this solution, and it's less likely the water will re-evaporate, right? Because you've got these non-volatile components in here. And the vapor pressure of the solution is always less than the pure solvent because of the influence of these, where's my pointer, of these non-volatile components. So eventually you get everything over on the other side. Magic. So here's an expression of why that thing happens. This is Raoult's law. There it is right there, R-A-O-U-L-T. Raoult's law says the vapor pressure of the solution above the solution in a closed container is proportional to the mole fraction of the solvent times the vapor pressure of the pure solvent. That's what this little 0 means. So this is the vapor pressure of the pure solvent, and if you add a solute to it, it will decrease its pressure to this value based upon the mole fraction of the solvent. Okay, so do we have a problem to work here? No, it doesn't give us a problem. That was Henry's law. Raoult's law is this one. Yeah, so this is the vapor pressure of the solution, this is the pure solvent, and this is the mole fraction of the solvent. So if we have a solution where we have calculated the mole fraction of the solute, and it's only got one component, the solute is mole fraction is say 0.2. So what would the mole fraction of the solvent be? It would be 0.8. So what we need is the vapor pressure of the pure solvent times this value gives us the vapor pressure of the solute. Now, for this case, the solute must be non-volatile, like a dissolved solid, like sodium chloride, something like that. If you dissolve something in it that has a vapor pressure of its own, then you have to modify the formula to account for both of them. And that's what this This formula here does. I'll get to it in a second. So, under ideal circumstances, as the mole fraction of the solvent increases, the pressure of the solution, the vapor pressure of the solution increases until you get to mole fraction of 1, and that is the vapor pressure of the pure solvent. So if you have two liquids together, now we're talking about liquids, not gases. If you have two liquids together and one of them is volatile, actually both of them, excuse me, both of them are volatile, then you have to modify Rayleigh law to account for both. But the total pressure, remember Dalton's law of partial pressures. In any gas mixture, the total pressure is equal to the pressure, the partial pressure each of the gases that are mixed together, right? So here we have the total pressure, and this, according to Dalton, would be the pressure of one component. This would be the pressure of the other component, if you only have two, right? If you have more than two, that formula can string out, you know, to as many components as you have. But what do you need? Well, you need to know the pure, let's say B is the solvent and A is the solute. So the solvent pure pressure is here and its mole fraction, and the solute pure vapor pressure is here and its mole fraction. So mole fraction A, mole fraction B should add up to 1. Now this is what it would look like under ideal circumstances. Notice that as we increase the mole fraction of A, the partial pressure of A would increase. That makes sense. If we increase the partial pressure of B going the other direction, then the partial pressure of B increases toward its pure, right? So this represents pure B and this represents pure A. In between, you have the mixture, right? So this is the partial pressure of A at some point where you have this mole fraction of A and this mole fraction of A and this of B. Then you add them together. You say, go from here to here and add them both together and you get this line. And that line is easy to derive. All you need to know is the pure of A and the pure of B and connect the dots. Connect the straight line. That's ideal response. So what do you have to have for an ideal vapor pressure graph of a two-component system where both are volatile? You need to have a system ideal where they do not interact with each other at all. They just act like billiard balls, right? They just, there's no intermolecular force involved at all. Some solutions behave that way, but more often they either interact with one another, in which will, if they attract one another, then the higher the combined concentration, the closer you get to enough of one and enough of another to have serious interaction, then you get this dip.
Are you still there?
Right? This concave in that ideal line. Okay?
Now again, I'm with Disability Advisor regarding insurance, and my callback number is 866.
If they repel one another, then you get the convex curve. It increases the vapor pressure because they're pushing against each other. They're not just leaving the surface under the influence of temperature and the consequent kinetic energy. They push against each other and elbow each other out of solution. Okay? So When you get to the middle of the curve, you have this increased vapor pressure, total vapor pressure, right? So an ideal situation would be where you just simply add the vapor pressure of one to the vapor pressure of other as calculated, and you get a value. If you measure the vapor pressure to be higher than you expected, then you find that those two have, let's see, maybe I got it. Oh, okay. No, when we say weak solute-solvent interaction, that can also include repulsion. Actually, that's a bad choice of words. We shouldn't say weak. We should say repulsive interactions. If it's truly weak interactions or no interaction, then you should get an ideal solution. But if they repel one another, you should get that bulge up, and you should have a higher measured pressure than the one you calculate. Or if it's lower than the one you calculate, you expect that there is a strong attractive force between the solute and the solvent. So this is just an expression of the different possibilities. If you have no interaction, the delta H of the solution is virtually zero. Then you have an ideal solution, and one possibility for that is benzene and toluene. Right? They're both volatile liquids, but they don't attract and they don't repel one another. They're ideal. If you have a negative or an exothermic delta H of solution, what that means is that the attraction of the two components is stronger than the attraction of themselves to their brothers and sisters, so to speak. So B attracts B, A attracts A, but when you combine them, A and B attract each other stronger than either A attracts A or B attracts B. So in that case, you've got a negative deviation, a dip, because acetone and water attract each other strongly. But if you have a solution where they repel one another, right? So the interaction of A and B is less than it would be for the individual components, then you have the convex, or the increase above what you would calculate. An example of that is ethanol and hexane. Ethanol and hexane are soluble in one another, right? There's still enough nonpolar characteristic of ethanol to make it soluble in hexane, because hexane is a nonpolar solvent. But they repel one another. Right? There's sort of a love-hate relationship. They attract enough to make solution, but they just as soon get away from each other. And that gives you a positive deviation, the upward bulge. Okay, let's see. I don't want to run out of time, so let me see if this is worth spending time on. Yeah, possibly we should. Okay, would you expect ideal or positive or negative interaction for these various ones? Let's see if we can find one where the interaction is ideal. That is, there's very low energy input, very ideal situation. It looks like C would be that one. Whereas hexane and chloroform would tend to be repelling one another. And ethanol and water would be attracting one another. So this attraction would be a negative deviation, A would be a positive deviation, and C would be ideal. Now let's see if I made my guess right. Oh, it didn't tell me. Shoot. Okay, you have to take my word for it then. What did I say? Positive deviation.
Yeah.
Negative deviation, and ideal. Okay, what's a colligative property? Colligative is sort of I think it's actually from the Latin, and it means a collective property, implying that it really doesn't matter how much of the solute you have in the solvent, you still get the same response. So examples will probably be a better way to explain that. And the three most common ones, the ones that we're interested in, are boiling point elevation. So if water boils at 100 degrees when it's pure, then if you add some solvent to it, like, I don't know, ethylene glycol, stick it in your motor, in your cooling system in your car, that allows your car to run hotter without boiling. Right? So we increase the boiling point. In fact, it's a very high concentration. It's usually 50% ethylene glycol in water. We'll elevate the boiling point enough so that the system will pressurize, but it won't produce gas, which would be catastrophic in an engine. And actually, there are safety devices built into the cooling system so that if it ever does boil, then it'll release the pressure. And you'll know it pretty quick because you'll see steam coming out from underneath your hood. So boiling point elevation, and we could do that. We could increase the boiling point of water with 50% ethylene glycol, excuse me, brain freeze. Or we could use anything else that would dissolve in water. We could use ethanol, for that matter, or isopropyl alcohol, as long as we would establish the same molal concentration, because we're dealing with temperature here, right? Same molal concentration, we would get the same boiling point elevation effect. Freezing point depression, similar. We decrease the freezing point of water by adding a solvent to it, and that's how we melt ice on our sidewalks. Right? We throw a salt out there, and gradually it dissolves in the water. Anytime you see ice and snow out there, it's going through microscopically through an equilibrium shift from liquid to solid, back and forth, back and forth, back and forth. And if you have the solvent there, then whenever it turns to liquid, the solvent goes, say, now you're mine. You can't freeze anymore. So it decreases the point on a macroscopic scale at which the solution will freeze. We do that with making ice cream too, right? You have ice around the custard container, and then you throw salt on it, and it decreases the temperature. Osmotic pressure is a little bit different. We can change the osmotic pressure. We have to explain what osmosis means. So if you've had any, say, biology or A&P courses, then you've had a rudimentary explanation for osmotic pressure, but we're going to be quantitative with it. And I'll save that till in a few minutes. So this is the formula that we use for boiling point elevation. Right? So the elevation in temperature at which the solution will boil is this delta T. Right? This is the molal concentration of the solute. So many moles of the solute per kilogram of the solvent. And K sub B is the boiling point elevation constant for the solvent. So that does change with the solvent. You would have a different value here for water or for alcohol of some kind, various solvents. So that value is unique, to the solvent. But beyond that, all it cares about then is just how many moles of the solute are there. Doesn't care what it is. As long as it's soluble in the solvent, then the only thing that matters is the concentration of the solute. Freezing point is a similar expression, freezing point depression. So the value you get here might be a positive number, but you use that to decrease the value of the freezing point by that factor. So you would subtract this from your freezing point of the pure solvent. And the units of measure are the same here, Molal. We have a different value here, even if it's water, boiling point elevation will have 1 K, freezing point depression will have a different K. So this is trying to explain what's happening, right? If this is a phase diagram, I think. Pressure, yeah, we should have solid over here, liquid here, and gas here. So what's happening is you're shifting the entire phase diagram curve down. So the triple point moves from here to here, and then the boundaries between liquid and gas are here for the boiling point change, and the freezing point change here are shifted to the left. Okay, I'm about to run out of time. I'm going to make a quick search. Let's see, where am I? Freezing point, boiling point depression. Okay, I just want to get a picture, a mental picture of that so I can come back to the same place. 1, 2, 3, 4, 5. Okay, we might make it. Okay, so we have a solution that is prepared by dissolving 25 grams of glucose in 200 grams of water. The molar mass of glucose, we're going to need that because we have to know the number of moles of glucose, right? And we need to know the mass of water, which we do. We have 200 grams. What's the boiling point of the resulting solution in degree C? And it's important that the glucose does not dissociate when we dissolve it. So what would happen? Let's say you have a mole of glucose. When you dissolve it, what do you have in solution? You still have a mole, right? If you have a mole of sodium chloride and you dissolve it in solution, how many moles of solute do you have? Now you've got 2, because you've got independent sodium ions and independent chloride ions, right? So you have to take that into account when you calculate the molal concentration of your solvent, solute. Okay, so we have 25 grams of glucose, and we want to convert that to moles, right? So what's the molar mass of glucose is given 180.16. So we get a certain number of moles of glucose. 25 and 180.16. So I get 1.388. 1.388 times 10 to the minus 1 moles. Okay, now we've got our solvent is 200 grams. So how many kilograms is that? That's 0.2, right? 1,000 grams in a kilogram, and 200 ratio to 1,000 is 0.2. So you have 0.2 kilograms, right? So that's the information that we've got. Okay, so I gave you a peek at the answer. Our formula is what? Delta T is equal to, and this is boiling point elevation. So we have K sub B times the concentration of our solute. So what's case of B? It's not given, right? So we have to look it up. So I got to go. I got to go online and look it up, unless you can find it in your book. So the Molal constant, freezing, no, I need Molal constant for boiling, for water. Here it is. Okay, boiling point elevation. Let's see if I can do it without having to dig into these things. Yeah, I guess I will have to. Okay, what's the value? Here it is. The for water, it's 0.512. Now, what are the units on that constant? Right? Because the units are going into the calculation too, and we don't want to end up with the wrong units in our answer. So as it turns out, this is 0, this is degrees centigrade per molal. Right? So the molality is 1.388 times 10 to the minus 1 molal. And that will give us our temperature. So I need to multiply this times 0.512. And that's 0.07. Is the boiling point elevation. That means the boiling point is that much higher than 100 degrees. So the answer to the problem is actually 100.07 degrees C. I think I did that right. No, I didn't do that right. Why didn't I do it right? Let's see if I did my calculations right. Hold on. 25,180.16 divide. That's right. I transposed it correctly. Maybe this is the wrong number. No. Oh. You see what I did wrong? Flunked my own test. I just calculated the moles. I didn't calculate the concentration. So in 200 grams of water, it's this divided by 0.2 kilograms. So that's what goes in here. So that divided by 0.2 is 0.6938 molal. Haha, there we go. Now this times that should be right. 0.35. So do we have the right units of measure? Well, yeah. This cancels. This is in the numerator. So that cancels that and leaves us with degrees centigrade. Okay? So the moral of that story is do like I say, not like I do. Now, sometimes you need a correction factor. If the Van Hoff factor, it takes into account dissociation of solutes when they go into solution. So ideally speaking, if your solute is, say, an ionic compound that completely dissociates in water, then the ratio is 2 ions for every 1 mole of compound. So the I would be equal to 2. But some of these I's have to be experimentally determined. Why? Because some dissociations are not complete. So you may think that your compound dissociates it from 1 into 2, but in fact, in solution, some of those ions reassociate. So instead of 2, it might be 1.8. But theoretically speaking, if you have a compound that dissociates in solution, the number of particles for each molecule is the ratio that you use. Say sodium chloride would be 2 to 1, calcium chloride would be 3 to 1 because there are 2 chlorides and 1 calcium. Let's see, what's another one? Let's say we put, oh, here's a good one. Say we put sodium phosphate. There you go. Because that's a 3 minus charge, that's a 1 plus charge, and it dissociates into 3 plus 1 is 4. So the I would be 4 for that one, theoretically. And that's what this is explaining. Sometimes you get ion pairing in solution, so that decreases the I value from the theoretical to some more realistic. And this has to be determined experimentally. You can't do that kind of work in your head. So here's the theoretical amounts for each one of these. I didn't even know that was going to come. So I equals 4 for this one. I equals 2 for that one, 2 for this one. Why is it only 2 for this one if you got potassium, nitrogen, and oxygen? What does it dissociate into? Only 2 ions. This is a polyatomic ion, right? So don't forget what you've learned from the first semester. The polyatomic ions, they act as a single unit. Okay. Ion pairing becomes really important when the solutions become more concentrated because there's more chance of interaction of the ions. So you get the probability of pairing is much higher. Dilute solutions, they behave ideally. So there's your modified equation, and you just substitute the different K, either the KB or the KF here. And I'm not going to, you can use, in fact, one of the labs, I think, uses colligative properties to determine the molar mass. Yes, the first lab, molecular weight by freezing point depression, uses that formula to determine the number of moles of the solute that are actually in solution. So we rearrange the equation to where the molality is the unknown. And then if you know the molality, you know the concentration of your solute, and you know the mass of the solvent, you can calculate the number of moles of the solute. Okay? And once you know the number of moles, all you need to determine the molar mass is what's the mass of the solute that you threw into that solution. And then you got the 2 answers, you can calculate the molar mass. That's lab number 1 in a nutshell. Okay, so this works out, you know, how you would calculate the molar mass from the data. And there I've given it to you, and I can't drag it on much longer, so I'm running out of time. So it's a good thing that it's there in black and white. Let's see. All right. This is I think this is converting one unit of measure into another. So this is the X for the sucrose, the mole fraction. It doesn't look quite as fancy as the other one. Okay, so osmosis, right? What do we mean by osmosis? Osmosis involves, and I think there's also a lab involving osmosis too. Let me see. No, that was first semester. Yeah, first semester we did the osmosis lab. Anyway, what is osmosis? First, we have to define what a membrane is. A membrane is anything that separates one substance from another. In our case, two different solutions or pure substances separated by a membrane. So the membrane has control about what moves from one to the other. If it's impermeable, nothing moves. But what we have in the case of osmosis is a semi-permeable membrane. Semi-permeable membranes allow the passage of water. Well, they also let gases through too, but we're concerned with water because we're going to have a solution on one side and ideally a pure substance on the other side. So we have water on one side and a solution on the other side. So that means on one side we have solute molecules and not on the other side, and those solute molecules will not pass through the membrane. So the only way that you can equalize is to transfer water, right? So the movement of water is restricted. It's decreased on this side because you have competition for access to the membrane from these solute molecules. So the water moves slower in this direction and faster in this direction. So when is equilibrium established? Well, equilibrium is established when you've got water moving this way the same rate as that way. Now, if there's no external force involved, right, no pressure here, then these will keep moving. If this is pure, these will keep moving until all of that's gone. But if we have a tube and a membrane here, and this is pure water, and there's our semi-permeable membrane, and initially we have the level, say here, and this is our solution, then water's going to move into that tube, right? And it's going to keep moving up as you add water to it. Keep moving up, moving up, moving up. And eventually it stops. Say it stops there. So what's the pressure on that solution? It's the difference between here and here. And you can calculate it based on the density of water and the height of the column and the diameter of the column. But there's a pressure there. So that pressure is providing enough pressure to drive water back the other direction. And eventually they reach equilibrium. So that's the osmotic pressure of that solution. And the higher the concentration, the higher the pressure is required to establish equilibrium. So the osmotic pressure is related to the concentration of the solute. Okay. Let's see. And the expression is in terms of, I thought the expression was in terms of molarity, not molality. Oh, okay. We haven't got there yet, sorry. Wrong slide. Okay, now osmosis, pardon me. We represent the osmotic pressure in atmospheres as the capital letter pi, you know, like pi r squared. We use the same letter there, but this pi doesn't mean 3.147 blah, blah, blah. It's actually equal to, it's a calculated value equal to the molarity of the solution in contact with pure solvent times the gas constant. Now, which gas constant will we use? Well, this is the key right here, atmospheres. We would use the one that has atmospheres in it. So it'd be 0.08206 liter atmospheres per mole K. That would be R, the gas constant. And then T is the temperature in Kelvin, right? Because the gas constant is also in Kelvin. So there's your formula, and there's the picture I just drew you. And there's another way of expressing it. The difference in the height between the pure and the solution is an expression of the osmotic pressure. Now this one can also have an I, a Van't Hoff factor, as part of the calculation if you have a dissociating solute. Okay, I'm out of time. Let's see, do I give a complete explanation here? Good. Okay, so you can review these slides and you can see the calculation that was performed, right? We had to adjust units of measure, right? We had to make sure it's atmospheres. And this is actually, we determined the osmotic pressure first, and now we're going to fill in what is this value and use that value to determine the number of moles of solute. If we know the moles of solute, the mass of solute, we can calculate the molar mass. Turns out for this one, it's 106 grams. Remember when we were doing empirical formulas and molecular formulas? We did the empirical formula based upon the percent composition by mass. But in order to do the molecular formula, we needed to know the molar mass of the compound. This is one way to find it, because you don't have to know what its formula is. You just use this colligative property and you can determine the molar mass of the unknown and use that to give you information for determining the molecular formula. Just a few words on colloids. Colloids are suspensions. They can occur as solids in liquids. They can occur as solids in gases. Like smog is a colloid. And I mentioned the Tyndall effect earlier. This is how you tell if you've got a suspension, and a colloid is a suspension. Colloid is based primarily upon the size of the solute molecule. So if the size of the solute molecule is less than 100 nanometers, 1,000 nanometers, excuse me. So that would be a micrometer, right? 1 micrometer or less. Then you can get colloids. What's an example of a colloid? Jello.
Mm-hmm.
Jello is a colloid of gelatin, which is a protein in your solution. And then, of course, you add other things that are actually in solution to make it sweet or tart or flavored or whatever. But the predominant particle in there is the protein, gelatin. Okay. Examples of colloids. Take a close look at these and see, you know, they have special names, some of them. Ruby glass is a solid colloid. It's not a solution. Some of these things you may not know that they are unless you're told. Where's smog? The fog is a gas and a liquid. That's okay. Smog should be in there too. No, smog is a solid in a gas. So where's a solid in a gas? Here we go. Marshmallows, polystyrene foam, and smog is a solid in a gas. Coagulation is a way of destroying a colloid. Colloids very often will be very stable over time. So once you've established your jello, it takes a long time to go bad, as long as you keep it refrigerated. Coagulating works particularly well with proteins, but it can work with other polymers. And you do it, one way is to heat it, destroying its structure so it drops out of solution, drops out of suspension. Adding an electrolyte, so you change the electrical qualities of the colloid particles and they cling together, and that makes them big enough to fall out of solution. Heat, electrolyte. You can also change the pH, you know, make it acid or basic, and that'll do it too. Okay, I'm a little over. Let's see, I need to unshare this, stop the share. There we go. Okay, so let's see, what do we got on the agenda coming up? Is it just these two chapters on the first exam, I think? Well, your 3 chapters, 11, 12, 13, my 10 and 11. So for exam 1, we're covering liquids and intermolecular forces, solids, and properties of solutions. But the next time we meet, we'll do a review. And the best way to review is to go into Blackboard and look up those review documents. The review document for this exam with the key and with the worked problems, and review those, because that'll be the foundation of our review discussion next week. Okay?
Okay.
Have a good week.
You too.